A ladder is attached to a hinge on the floor and is leaning against a box, pressing the box against a vertical wall. I guess most walls are vertical. Friction between the wall and the box is mu static of 0.43, and this prevents the box from slipping. There is no friction between the ladder and the box, which is good. Well, convenient for calculational purposes. The ladder has length of 4.5 meters, mass of 7.5 kilograms, makes an angle theta, which is 50 degrees with a horizontal floor as shown in the figure below, to the right. The box has a mass of m. Bum, bum, bum. What is the magnitude of the torque about the hinge due to the weight of the ladder? Okay, so when I see the word about here, I'm thinking this means that that's going to be the axis of rotation. And we're looking for the weight of the ladder creating a torque. So first thing to think here is, all right, this system is in equilibrium. It's not moving. So we're going to have a summation of all torques, which is going to be 0. And our two torques will be torque clockwise and torque counterclockwise. So we're going to have a massive ladder. I'm going to draw it at the center, straight down. This will be due to force of gravity. There's also going to be a normal force normal. That's a terrible N. I was going to do a lowercase n, and I decided to do an uppercase N, and it turned out tragic for both parties involved. So this is going to be about the axis right here, axis of rotation. This is going to be the torque clockwise, and this will be the torque, and it looks like a tension. Torque, let's see, the other way will be counterclockwise. And so the torque due to gravity, about the hinge due to the weight of the ladder, that is going to be the one we're looking for right now. And I do it at the center because if you have a line like this, a line of mass, then you can just average the top and the bottom. I'm not going to go into really why that is right here, but it is true. Basically, you average this one, and it gets to the middle, average that one and that one, also gets to the middle, keep doing that until you get to the middle, and then that's what you have for your mass. So another thing to kind of consider, or at least keep in the back of your mind, is there's no linear motion as well. So the sum of all, that's a summation, of all forces will also equal 0. So when you see this force normal over here, it might mean that down this hinge it's taking up some of the other force here. And so there's probably also going to be a force this way on the hinge. We're not concerned with that because that's just showing, all I'm doing there is I'm showing that these forces here, the gravity and the normal force, there's other forces involved, so it's not moving linearly as well. Just like with the summation of all torques, if that equals 0, you have no net angular acceleration. Same thing with linear. So don't think just because we're not addressing the linear that the linear doesn't exist. Okay, back to the problem at hand, blue. So torque equals R cross F. Torque equals R cross F. And this is the radius starting from the axis of rotation. And then this is the force. And this cross product, it's often thought of as sine of theta, which is the theta between the two angles. But an easier way to think of it, at least in this terms, is the R times the perpendicular portion of R times F. Okay, we'll do it this way. And this is now multiplication, not dot product, just multiplication. And okay, maybe these probably shouldn't be vectors. There we go, magnitudes. So we're going to use the perpendicular portion here. So force goes straight down, gravity makes sense. And then the perpendicular portion of this triangle will be this part right here, which is actually going to be cosine of theta. So I'm going to worry less about the formal definition of cross product, and I'm going to do it more in a logic intuitive sense here. So we have cosine of theta. So the torque due to the ladder will be okay, so it'll be the length of the ladder over 2, because we're looking at the center point, times the this we have theta is 50. That is 50. that right there, theta equals 50 times cosine of 50. And then we're going to multiply that by the force, which is mass times gravity. So mass the ladder times gravity, which is, all right, now I know this is so sideways, 4.5 and 7.5. So we have 4.5 over 2 times cosine of 50 times mass, which is 7.5, times gravity, which is 9.81. Grab a calculator, on, mode, make sure it's in degrees, that's excellent. So we'll do 4.5 divided by 2 times cosine of 50, close the parentheses, times 7.5 times 9.81. Looks reasonable, and we get an answer of 106.4 equals 106.4. And since this is torque, this will be Newton meters. Oh, see if that's a possible answer. Bum, bum, bum. 106 is, and that's what I'm going to go for. And just to be a little bit extra careful, counterclockwise. You don't need to write that in, because they ask for the magnitude. So making it a vector, counterclockwise. Okay, so bum, 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 bum. Yeah, I like that a lot. Okay, what is the maximum mass of this box that can have? What's the maximum mass the box can have before it starts sliding down the wall? Okay, so now we're going to look at this box, and so we have force gravity, then we have force friction, and the idea here is this force of friction is going to be related to this force normal. And do they give us a force normal here? They don't. Interesting. Well, we know that this force normal has to be related to gravity and torque and something. I'm just going to go with this. So, I don't know what to do, but I do know that there's a relation between the torques. I'm going to start by saying that torque clockwise equals torque counterclockwise, because we have this torque here and that torque there, and if we set them equal to each other, just kind of run with it, it might tell us something useful. So, the torque counterclockwise is going to be, so I'm going to look at this side. We've already solved this portion over here, it's 106. So this would be R cross F, which the radius, the force normal will be this. So it's force normal. And the radius will be L. So we have L cross force normal. So I'm going to first look at this real quick right here. So this is the radius right here. This is R. I know, so messy. You're right. I should clean this up slightly. Whoop. I should probably clean it up a lot. So the idea here is we're looking for torque clockwise. And that's going to be involving force normal here and this radius right here. And so what we do want is a perpendicular, so R cross F. So we want this value right here. So this is theta. This is 90 minus theta. So this is 50. So that makes this is 40. And so we're going to do the cosine of this angle to get this angle right here. And this value right here will be the perpendicular value to force normal. To the force normal. So clean this up real quick. So this is going to be, I think I'm probably just going to write the exact same thing. So this will be the length L times, and this time we're not going to use L over 2 because it's rotating about the end, times cosine of 40, which is the same as sine of 50, times force normal. Okay? So we know what this is, we know what that is. We don't know what force normal is, but I think we can figure it out here. So we have force normal here, we have force of friction here, and we have force of gravity here. And we know that force of gravity and force of friction will equal each other because the box isn't falling. That's just one of the assumptions. So we have, change thought process here. Ooh, green. We've already done green. Light green. This is kind of a disgusting green color. That's okay. We're going to go with this. Force friction equals, I'll make that a capital, equals force gravity. Force friction is static force of friction times normal force. Excellent. So that's one of the things we want. And this will be times mass times gravity. Excellent. That's something else we want. So rearranging this, I know, many arrows. So we know that force normal equals mass times gravity over mu static. So we can replace this up here. We get L times cosine of 40 times mass times gravity over mu static, static coefficient of friction. And then, as we discussed previously, this is going to be equal to, right there, torque clockwise, which we do know because we just solved that in the previous problem. Rearranging for mass, we have, so messy, maybe just down here. Mass equals torque clockwise times mu static over gravity times length times cosine of 40. Okay, writing this out in numbers, we have 106. I think this is 0.43. I think I read that right. I'm going to look real quick. 0.43. Yep, and then we have a length of 4.5. Whoop. Over 9.81. 4.5 cosine of 40. Extend the line. And this will give us an answer. Hopefully. Ideally. So we have 106 times 0.43 divided by massive quantity, 9.81 times 4.5 times cosine of 40, which could be sine of 50, that's fine. And then I'll do parentheses, and that gives us 1.353. 1.353, and this will be in kilograms. Okay. There we go, finish off the box. 1.35 kilograms right here. Excellent. So that is the answer. So to backtrack what we did here. So the first thing first part just asked us for the torque about the hinge to the way of the ladder. So we had ladder, we did center of mass downward, and we just used the equation torque equals R cross F. Not too bad. Where R, this part right here, is the part of the radius that's perpendicular to the force. You can get more. Cross products are normally thought of as sine of theta, where theta is the angle between the two vectors. It's easier to just think of the perpendicular portion. We did that. Then we asked the second part about how much does this box weigh? No idea what to do, but we did know that torque clockwise equals torque counterclockwise, and we kind of worked through that for a while. Then we got stuck because we didn't know what the force normal is right there. And we're like, well, okay, what else do we know? Well, we also knew that force due to friction would equal force due to gravity holding the box up. And from there, then we were able to kind of figure out the rest of it, and it magically worked out. Mostly algebra and a little bit of persistence. And this is the maximum mass. It could be that it's holding up the box, and the box is just really light and it's really heavy ladder. This is the maximum mass that it can be before it starts sliding down the wall. So I hope this helped. I will see you guys next time.